Hi, thanks for joining me. Today I've got a really interesting number theory problem from the USA MTS. And this problem is quite nice because the solution involves some theorems which you wouldn't maybe expect to use in this sort of problem. Anyway, we call a positive integer uphill if the digits in its decimal representation form an increasing sequence from left to right. And for this problem, we'll be working base 10. So for example, 123 is an uphill integer because the numbers increase as you go from left to right. Same with 114. So you are allowed, they don't have to strictly increase, just has to be non-strictly increasing. Suppose we have a polynomial p of x with rational coefficients, and it takes on integer values for every single uphill positive integer x. Is it necessarily true that p of x takes on an integer value for every integer x? So suppose we have this polynomial p of x such that whenever you plug in an uphill integer, the output is also an integer. Is it true that if you were to plug in just any old integer into p of x, you're guaranteed to get an integer? Now, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. Okay, so it turns out the solution is no. And we're actually going to prove this by constructing a polynomial p of x, which is an integer for every uphill integer, but there are some integers which aren't uphill, which when you plug them in, the result will not be an integer. The way we're going to prove this is first by making an observation. Uphill integers can be written as the sum of other integers. So if we consider the numbers b1, which is 1, b2, which is 11, b3, which is 111, and so on, just adding a 1 or placing a 1 at the end each time. What we notice is that every single uphill integer can be written as the sum of these bi's. So for example, 459, that would be 4 lots of 111 plus 1 lot of 11 plus 4 lots of 1. Like so. And hopefully you can see why this is the case, basically, or how I've kind of constructed this sum. The way I've done it is by firstly looking at the kind of biggest number, so the leading number here, and that's 400, so I need to use 4 lots of 111, and I know that this won't overshoot my number because of the fact that it is an uphill integer, so this number here will be at least 4, and same with this guy here. And then you're left with a slightly smaller number, and you can kind of continue inductively. So every single positive integer can be written as the sum of these guys, and in fact you can further insist that you only use at most 9 of these guys. So here we used exactly 9, so 4 plus 1 plus 4, but you don't have to necessarily use all 9, but you can always do it so that you use at most 9. And this is a key observation. And what we notice again about these bi's is that if I is even, then bi would be like 11 or 1111 and so on. And all of those are going to be multiples of 11. So they're going to be 0 mod 11. And if I look at if I is odd, we can see that bi is congruent to 1 mod 11. So for example, 1 is obviously 1 mod 11. 111, well, that's 1 more than 110, and so on. And so what does this tell me? This tells me that, well, if you add up 9 of these bi's, you could get any number between 0 and 9 mod 11, but you would never get 10 mod 11. So we can conclude that therefore any uphill integer is never equal to 10 mod 11. And this is our inspiration to create a polynomial p of x. Okay, so we've proved that if u is an uphill integer, then u is not 10 mod 11. And now if we stare at this for a second, we might start to think of Fermat's little theorem. And now we're going to make an observation here. Let's consider y minus 10 to the power of 10. And here y is just going to be just any old integer. And what could this be? Well, according to Fermat's little theorem, this is going to be 0 mod 11 if y minus 10 is congruent to 0 mod 11. So this here is mod 11, I should say. And it's going to be congruent to 1 if y minus 10 is not congruent to 0 mod 11. So we have essentially like an indicator function. This thing here, if we plug in what y is, it basically tells us whether or not y minus 10 is a multiple of 11 or not. And this is just as a result of Fermat's little theorem. So this kind of motivates us to use this function here, p of x, which is just going to be x minus 10 to the power of 10 minus 1 divided by 11. And I claim that this is a polynomial which kind of satisfies this property here. Clearly it's a polynomial with rational coefficients. And now what do we notice? If u is an uphill integer, well then we know that u minus 10 to the 10, well because u is uphill it's not 10 mod 11, so according to this u minus 10 to the 10 will be 1 mod 11. And so if I plug in u here, p of u would be some number which is 1 mod 11 minus 1. So the numerator here will be a multiple of 11, and so if I divide by 11 this will definitely be an integer. However, we can clearly see if this is not going to be an integer for every single value of x. Clearly, if you just plug in x is 10, this thing here would be minus 1 over 11, which obviously isn't an integer. And we arrive at our solution here. So a really interesting problem, and I don't, when I first looked at this problem, I wasn't really expecting Fermat's little theorem to come up in the solution, but I think this is a really, really elegant way to prove this. If you want a bonus challenge, I encourage you to answer the same problem but change the word uphill to downhill. So a downhill integer would just be if the numbers are non-strictly decreasing. So for example, 987 is a downhill integer, or 995 is also downhill, and see if you can do something similar here. It's a little bit more challenging, but I encourage you to have a go. Let me know in the comments how you get on with that one. Anyway, thank you for watching. If you're new to the channel, please do subscribe if you haven't, and do give this video a like. I'd really appreciate that. Apart from that, I'll catch you in the next one. Have a great day.